All right, so just a brief review of antiderivatives. Nothing crazy. There are some concepts, some rules, and things like that that you should know from Calc 1, but we'll cross those bridges when we get to them, I think. Okay. Some of them, if you look at the bottom of this page, are I call them the obvious ones. The basic trig functions, things like that. But then there's some other ones that we'll talk about too. All right, so we talk about an antiderivative, which is anti-differentiation, going the reverse process from actually finding a derivative. A very simple case, x squared is an antiderivative of 2x, but we know it's not the only antiderivative of 2x. Right? That's where the plus c comes into play, because it could be x squared plus some other constant c. All right, it could be x squared plus 4. It could be x squared plus 12. When we get into, we will not get into it, but in Calc 3, when you get into multivariables, you can treat another variable as a constant. So there are some circumstances where another variable could be treated as an add-on to an antiderivative, but that's a little bit of a teaser for, let's say, March of 2019, if you're in Calc 3. Any two antiderivatives of f will differ only by a constant, which makes sense. All right, I don't know if you have any experience with slope fields from Calc 1. It's not always in the curriculum, depending on where you go, who you have. But we'll look at it here. It's a graphical display that gives us a sense of what all possible antiderivatives would look like. Right. So we have y equals x squared, the notation y equals x squared plus c, then dy dx equals 2x. That's known as a differential equation. Right? So in reality, you've been working with differential equations for a while, so you think, well, how is that the course that follows Calc 2 if I've already learned it? Well, it's a form of an equation. It's a differential equation, which would then be in differential form. It's what you do with those differential equations that dictate the level of difficulty. So the whole course called differential equations is basically just referring to courses that are equations that are in that form. From that form, we can do a lot of different things. That's where that actual course comes from. All right. We could write it as dy equals 2x times dx. That's the differential form of the differential equation. All right. And when we're taking an antiderivative, that's actually what we're looking to do. All right. And I'll explain a little bit more about notation as we go, because I know with Calc 1, antiderivatives is usually kind of like a little bit of an add-on at the end, where it's like, let's spend a whole lot of time talking about derivatives, and all right, we got 2 class sessions left. Let's do some antiderivatives. That'll get you ready for Calc 2. Well, depending on your teacher in Calc 2, it might not. So some people are like, well, you learned this last semester, and if you didn't, well, teach yourself. So that's where I was. Anyway, we have this integral notation here. So you can just read through this on your own if you want. The integral sign is something that you've seen before. It's not anything that's new. The funky S, that just stands for it's taking the antiderivative or the integral of a function. And you may have learned that dx is talking about what variable that you're integrating is. So this would be saying find the antiderivative of the function f of x with respect to x. Right? That's the commonplace way of saying it. Right? So with respect to x. And that's all well and good. Just like when we were taking dy dx, the derivative of y with respect to x, we would always say with respect to, I don't know. I'm assuming that's the case. It's historically the way it's been taught. But that's not really true. It's just a lot easier to say than the derivative of y per incremental change in x. That's kind of a mouthful. You don't want to say that. You got like 10 lines of equations to read off to somebody. Every time you see a dy dx, derivative of y per incremental change in x, especially if you have something that's in implicit form. So you'd have x dy dx plus y dy dx plus sine of x dy dx. Every time you see a dy dx, are you going to say derivative of y per incremental change in x? Probably not. So you say with respect to x, the reason you say it that way is to indicate what the important variable is in the derivative. Same thing with antiderivatives. So what we're talking about here is an area, right? And so you have a function that represents a height. What the dx represents is an incremental change in x. You have a height with an incremental change in x that's going to create a rectangle, which will give you an area, all right? But a single area. Now, if you have an interval, like, let's say, going from 0 to 10, then you're not necessarily going to have just one incremental change. You're going to have many incremental changes from the start to the end. So you're not just going to have one rectangle, you're going to have a bazillion rectangles. What the integral symbol does is it tells us to integrate all of that. So collect all of them together, put it all together, and come up with a combined area for that interval. Right? That's what we're talking about there. But we'll get into it visually down the line, but intuitively that's really what it's saying. So it's basically saying these two guys here are talking about the area contained under the function f of x per incremental change in x. All right? So simply multiply by the incremental change in x to give you the total areas. All right? And so that's what we're really dealing with. All right? But in terms of just commonplace getting the job done, performing a calculation, we just think of that funky s as this indefinite integral, which means the antiderivative of f with respect to x. But you don't want to lose sight of what it's really talking about. You have a height based on where that curve is. So the curve is living off in space somewhere. You got the x-axis. F of x is right here. So x comma f of x. It has a particular height. Now, if I want an area, then I would want some incremental change in x that I would call dx. That gives you a single area. Collect them all from the beginning of your interval to your end, and you have what you're looking for. All right. Now, some subtle things. Just going back to Calc 1. Maybe it was talked about, maybe it wasn't. I can promise you that the first time I taught Calc 1, I think it was in 2000, had to be 2004. Whatever. I did not emphasize stuff like this. I don't know if you had a teacher who's been doing it for decades, or if a teacher that just came out of college and just barely knows the stuff, him or herself. That sometimes happens, believe it or not. So the delta x, capital delta, the lowercase delta, that looks like a d. It is a d. I wrote a d, but that's because I don't want to write a Greek delta, lowercase delta, over and over and over again every single time I want to write a dx. All right. So when we're talking about a delta x, we're talking about a change over an interval. When we're talking about the lowercase delta, well, it's smaller, so it should represent something that's smaller. Incremental change. It went off. Crikey. That's frustrating. I'll maximize again, but just so at least that part is on the grid. All right, incremental change. You may have learned it as an instantaneous change, but what's an instant? How do we define an instant? I don't know. I kind of revised my way of thinking about things after I watched the Essence of Calculus series on YouTube. You know, there's a lot of good stuff out there. Some of it some better than others, and some of it is good in bits and pieces. And then there are some diamonds in the rough where it's like, well, this was good from beginning to end. And that's the essence of series. I think I might have mentioned this last class, but if I didn't, well, I'm mentioning it now. Essence of calculus, essence of linear algebra. It's 3 blue, 1 brown, 3 brown, 1 blue, whatever it is. But if you just look up essence of calculus, you can get into a lot of this stuff. And really the idea that how do you measure something that happens instantaneously? Like the slope of a line tangent to a curve. We call that, historically we've called it an instantaneous rate of change. But if you really think of it as the rate of change over a very, very, very minuscule interval, that actually makes more sense. Because how do you represent change instantly? If no time has elapsed, then how could there be a change in time? Right? The idea of a limit allows us to approximate what that rate of change would be if we ever got to a moment or a condition where there was no lapse in time. But since we can never achieve that, practically speaking, we can't really say instantaneous. What we can say is over a very, very infinitesimal or minuscule amount of time. All right, so that way of thinking kind of drives the idea of the dx versus the delta x. So something on a very small interval is really what the name of the game is here. And that's going to be the recurring theme throughout the unit. Because if you figure out something on the micro level, then we can integrate it out to cover the macro level. Right? So if I'm looking for the volume of a cylinder, find the volume of one component of that cylinder, then maybe I can extrapolate out to figure out the entire thing. That's the idea. All right, but before we can really get too crazy into that stuff, we need to actually do things like find antiderivatives. Because application is wonderful, but it's not the only thing. Sometimes, well, there's also math for the sake of math, which I'm a big fan of, but it's not always profitable. Math for the sake of applying it is really where most people come into play. But also, I mean, the concept of finding an antiderivative or a derivative, I mean, that's a necessary evil when it comes to being able to apply this stuff to some sort of field, whatever it is you're looking at. So we'll talk about rules of integration, and then we'll kind of expand out from there. So does anybody know what the antiderivative of the number 0 is? C, yeah. Yeah, it's some constant. Any constant will differentiate down to 0. And again, if you're a little iffy on the concept of an antiderivative, just think about the answer having the derivative that is the integrand. Right? The integrand is the thing that's contained within the integral. Right? If you think of the funky s and the dx as your fencing, those are kind of like parentheses in the problem. Right? So you're looking at that as containing the thing you're looking to find the antiderivative of. Whatever you come up with as the answer, you should be able to check it by taking its derivative. So I'd be looking at this. I won't do this for everyone, but I'll do it this one time. I'd be checking it by saying, what is the derivative with respect to x of c? If it's 0, then I'm comfortable that I didn't just botch that up. All right. Hatched. Now, k is another way of representing a constant. It's just not a constant of integration. It's not any particular constant. It could be a constant of proportionality. It could be some other kind of rate of change, maybe associated with exponential growth. If you remember NOE to the KT from pre-calc, something like that. It's just some numerical value that we just don't have access to right now. All right. So what is the antiderivative of constant k with respect to x? Kx plus c. All right. And so this is a big one because before this unit's over, we're going to be tackling some problems where we have to figure out what the constants are in the solution to a differential equation. Right? So we're going to have to figure out not only the constant of integration, but the constant, in this case, of proportionality. So we'll have to make a determination on that. And oftentimes, that involves finding a logarithm, or using a logarithm, sorry. K lowercase f of x. What would the antiderivative of that be?
K of x,
K f of x, but this time capital, plus c. And that's the one thing I kind of glossed over. Just kind of hidden there. If I take the antiderivative of lowercase f of x, we write it as capital F of x. There is a hierarchy there. So if you kind of look at the progression downward, we would say f of x, capital, lowercase, then we get into our primes. Okay, so little tick marks to represent the primes, but then after you get to the third one, we start putting the number of the derivatives, of the fourth derivative, in parentheses. All right, but generally, this is where we start. Not necessarily. It can be, but since it's with respect to x, it's specifically in terms of x. If it was f of x comma y, then it would be an explicit function. I like to kind of equate this to like a building. I mean, I did it backwards. I should have put the capital F of x on the bottom, but if you think of this as like the basement, then you think of this as the ground floor, then the first floor, second floor, third floor, and so on. It's an apt analogy, because you would think that whatever tops your list would be the thing that you're starting with, but whatever you start with, you could always go backwards a level from there. You can go backwards 10 levels from there, but it's only practical to go backwards one level from there. And I'll explain why that's the case later on, but it has to do with identifying C. Right? Antiderivative of x to the nth. X and d plus c, yeah? Right. We all have varying experience with antiderivatives, but some of us have enough experience to have been burned by the plus c issue in the past. You forget to put plus c on a test, and I forget to give you full credit. Right, that's how it goes. Usually a half-point deduction. Depending on how many questions there are related to that, maybe a quarter-point deduction, but something minor. But yeah, it's important because x to the n plus 1 over n plus 1, beautiful, but not as beautiful as the answer, including the plus 6.
Why do you put it over?
Because when you find the antiderivative of the power function, you increase the exponent by 1 and then divide by the new exponent. So if I were to take, let's say this is x squared, it would become x to the third, but then I would divide by the 3. So we're just kind of building that into a formula. Some people write it as 1 over n plus 1 as a coefficient, and then x to the n plus 1. That's fine too, either way. I'm just thinking, we're not really going to need this particular notation until Unit 3, when we get to sequences in series, because it becomes pretty important when we get to Taylor and Maclaurin polynomials. But yeah, just having a sense of how to find the antiderivative of power function is pretty, I mean, it's usually catastrophic if you don't know. I shouldn't have said it's pretty important. That's not even close. Do we know the antiderivative of the cosine function? Sine of x plus c. Yeah, we're on board now. Antiderivative of sine? Negative cosine x plus c. And again, that's because cosine has a derivative equal to negative sine. So to offset that, we negate the cosine. That's like a minor correction that you're going to want to do from time to time. When we get to it in a little while, I'll call it baby U sub. But it's essentially the idea that you have a sense of what the antiderivative is. So you go for it, you make a note of what you think the antiderivative is, check it mentally by taking the derivative, and then do a quick course correction. Right? So let's say off the top of my head, I was thinking, okay, the antiderivative of sine is cosine. It's incorrect, but that's what I think. So I write it down, I check it. By checking, I get negative sign. I say to myself, well, that's the exact opposite of what I want. All right. So that means that I should negate what I thought the correct answer was. Right? A little correction on the fly. If I took a guess here, and my guess gave me a 2 sine x, so double what I needed, I'd slap a 1/2 in front to correct for that. You can do that when it's only off by a constant. If it's off by a variable, it's a different technique that's required, usually something more advanced like integration by parts or something along those lines. Antiderivative of secant squared. Tan x plus c. Very good. Cosecant squared? Negative. Yeah. Very good. Antiderivative of secant x tan x. What do we say? Secant x plus c. There's like an obnoxious amount of space between the secant x and the tan x. So if somebody, for both of them, if somebody wanted to submit that for typo bonus, I would take that. Cosecant x, cotan x. What do we get there? Negative cosecant x plus c. All right. Notice the relationship between cofunctions. Not only, sometimes, depending on how your Calc 1 experience was, it could have been like, here's some rules, memorize the code, and then there's some other cases where it's, here are some rules, but if you notice the relationships that exist, you can avoid having to study half of them, and I think this is one of those cases, because you notice how sine has a derivative that's cosine, the reverse is obvious. But it's opposites when you're dealing with a cofunction. Cofunctions always have negative cofunction relationship. So when I take the antiderivative, for example, of secant squared, I get tangent. So here's my cofunction of secant squared. It's cosecant squared. Its antiderivative will be the negative cofunction of the other. So cosine has an antiderivative of sine. So the cofunction of that, which is sine, should have an antiderivative that is the negative cofunction of this. So negate it, slap a co on it, and you have your answer. And that's what happened there. All right. So if you know the antiderivative of a particular trig function, then you know its cofunction's antiderivative just by negating and slapping a co, or removing a co from your cofunction. So if it was a co, remove the co. If it didn't have a co, put a co in. Okay. It's the kind of thing where if you already do this stuff, I'm kind of wasting my breath, but if you're a little iffy on it, maybe that's the thing that kind of gets you over the hump. We will see.